So all of this mean, variance, standard deviation is now going to apply to probability. Right? So we looked at it from just a data set. Now we're going to look at it in terms of probability. And it's pretty straightforward. There are some formulas that you're going to have to kind of work through and memorize, but we're going to work on it today and tomorrow, and then your quiz will be on Thursday. Okay? Expectation is the one that's a little trickier, and we're going to spend a little less time on that because it's not as important, but it's still important. Okay? First off, to find the mean from a probability distribution. That's the first thing we're going to do. So just like we could find the mean from a data set, we can take the probabilities from a probability distribution and their outcomes and determine the mean from that. And what we're going to do is you're going to take the sum of the product of the outcome and the corresponding probability. Okay? So meaning we're gonna multiply, that's product, multiply the outcome and the probability and add each one of them up. And that's going to give us our mean. Okay? And what the mean is, it's the averaged probability. Okay? We're going to start doing this with our same example that we had on Friday. Okay, so this is the same probability distribution that you had on Friday. And the difference is now we're going to find the mean. Okay. So all you have to do is take the product of the outcome. Remember, this is the outcome here with the probability. So you're really going to have, in this case, 4 products, and you're just going to add them up. So go ahead and do that and see what you get. So we're going to use that mu notation again, bless you. Okay, and again, we're just going to multiply the outcome with its corresponding probability and see what we get. Okay. Did anybody get the answer yet?
I got 3 halves. Yeah.
3 halves. In this case, 1.5 or 1.5. That would be the mean.
3 halves?
I would not leave it as 3 halves only because, especially in a practical sense, 1.5 has more meaning to us than 3 halves. And when we talk about mean as a statistic, we typically write it as a decimal. If you think back to all the times when we were finding the mean with data sets, we'd have some kind of decimal anyway. So typically that's what we're going to want to do. Now, the book also has some notation that I want you to see, just so you see this. That's what this means, okay? So this means the mean. This is the sum. Remember this summation? This capital sigma means add up. And you're going to add up the outcome, x, with the probability, that product. Okay, that's a scientific mathematical way of writing out the mean from a probability distribution.
Wait, can you say what those mean?
All the symbols mean?
Sum, yeah.
So this is the sum of the outcome times the probability.
Okay.
The capital sigma means sum of. I know some of you who are in calculus have seen that before. Okay. Just a mathematical way of all of this in words. Okay? All right. Questions? Let's get on to variance and standard deviation. If you recall, what's the relationship between variance and standard deviation?
Variance is the standard deviation squared.
Okay, so that's one look at it. Again, it talks about how spread out the data is. So variance does equal the standard deviation squared. Or what else? What's the
Something square root.
Okay. So let's take this and
Standard deviation is equal to the square root of variance.
or the square root of variance equals standard deviation. Okay. Just know that when you're finding these things, That's the relationship between variance and standard deviation. I will tell you that what we will be doing is finding the variance first, and then taking the square root of that to get the standard deviation. Okay? And that's just kind of review if you didn't remember that. I want to give you what the mathematical formulas are for variance and standard deviation in terms of the notation that we just kind of looked at. So it's very similar, but here's variance. Remember, variance was sigma squared? Okay. So what we have here is the sum of all of this minus the mean squared. So in order to find the variance and then consequently the standard deviation, we still will need the mean. Now sometimes they'll give it to you, but sometimes you're going to have to find it. And you're going to have to find it the way we just did on the previous slide. Okay. Now what this variance notation means here is that I'm going to find the sum of the outcomes squared. This is the only difference. So before when we found the mean, it was the outcome times the probability. For the variance, I take the sum of the outcomes squared. That's really the major difference there. Okay, times the probability, and then from that, I'm going to subtract the mean squared. So I'm going to have two calculations. This is one calculation, and this is the other calculation, and I'm subtracting those two things. Okay. Obviously, there's going to be a little bit of work involved here. And there will be a little work involved to find the mean, like we did on the previous page. And it's similar work. The squared is the difference, okay? Questions on that? Then once we find that, we're just going to take the square root of that to find the standard deviation. And that's all that says there. It's the same thing as what's on the left with all under the square root, okay? So let's look at a probability distribution and find these things. So here's we're still working on the same distribution, so copy paste. Okay, now we're going to find the variance and standard deviation. Okay, we already know the mean, because we're going to need to know the mean in order to do this. And now this is just on a different slide. You don't have to write this down again. It's the same stuff that was on the other slide. It was just, I want it there so we can see what we're supposed to do. Okay, now the only difference is I'm going to take the outcome, these numbers here, and square them first and then multiply them by the probabilities. Okay, that's the only difference to do this part. So this part right here, the sum of the outcome squared times the probability. So all we're doing, again, we're going to square these numbers first, then multiply them by their corresponding probabilities.
Okay.
Then we're going to subtract off the mean squared, which we just found out was 1.5 before. So why don't you go ahead and try to find the variance. Go ahead and try to do this and let's see what you come up with.
What did you say was step number 1?
Square the outcome and then multiply it by the probability. Just like it says right here.
But kind of like what we...
The mean was 1.5 if you didn't see that in your notes there. Okay, so again, I just took the outcome, I squared it, multiplied it by all the probabilities, and then I'm subtracting off the mean squared. How many had it set up like that? Okay, how many didn't have it set up like that and did something differently?
I didn't have it set up like that. I didn't do it that nicely.
Okay, so if you did the squaring and multiplying sort of separately, that's okay. Okay, let's just pay close attention here. So here's the outcome. So it looks just like what we did for the mean, except the outcome is now just squared. And that's going to come into play. Obviously 0 squared is still 0, 1 squared is still 1. It's really going to come into effect over here for this particular example because 2 squared is 4, 3 squared is 9. Okay, and then you just have to simplify all this down, subtract off, this is 2.25, and that's where you'll get your variance. Okay, what's the variance? What'd you get?
0.7.
Okay, 0.75. Now notice the notation. Okay, sigma squared is variance. Okay, now in order to find the standard deviation, all you have to do is take the square root of this now. So the key to these problems is there's sort of some sequence involved. Sequence being find the mean first. Once you find the mean, then you're able to find the variance. Once you find the variance, you're able to find the standard deviation. If you mess those steps up along the way, it's going to create a problem. So you just got to be very careful with your calculations. Be careful when you're plugging things into your calculator, making sure that you're doing that properly. Okay. So then when I take the square root of 0.7, okay, that's what sigma or the standard deviation is. In this case, it's about 0.9. I think it. Yeah. I don't know why I decided to put that one as 0.9 instead of. But if it's 0.86 repeating.
No, 0.660254038.
All right, so it really should be, if I want to stay consistent, 0.87. Okay. Question. So the reason I didn't put these answers in fractions is because when we talk about mean, we talk about variance, we talk about standard deviation, we're talking about a statistical calculation that we typically associate with a data set. And when we do that, we were typically pulling that from a calculator and we're getting a decimal. That's the reason for the inconsistency this time. Because when we talk about those measures, we want them as decimals. Let's do an example problem together in context, then we'll talk about expectation, and then we'll be done. Yeah, another one. Here we go. All right, so this is on page 263 in your book. If you would rather screenshot from your book, if not, you can take a picture of the screen. This is at the bottom of page 263. So here's what's happening in this problem. There's this talk radio show, and this particular station has 4 telephone lines. 4 telephone lines, okay? So, if the host is on the phone with somebody else, they go to one of the other lines and they stay there ringing on hold, or they can't get through it, that you get a busy signal. And I don't know if you even know what a busy signal is, but there's a different tone when when your phone call doesn't go through, okay? Basically, what someone would get is a noise that's different than the ringtone that tells them, you know what, there's no more lines available. Yeah, yeah. So that was common because there didn't used to be call waiting and stuff like that. And at radio stations, how many of you ever tried to call in and win something on the radio? Yeah, same kind of idea. Same kind of idea. Now. Okay, so here's the deal. They've got four lines, and then the probabilities of people getting through. So the probability that no one will get through is low. The problem that only one person will get through is actually quite a bit higher. That 2 people will get through, that 3 people will get through, that all 4 people will get through. Now that's really low, okay? And so the question that they want to know is, should the station have considered getting more phone lines installed? And so what we're going to do here is we're going to calculate the variance. We're going to use the standard deviation to find out how many phone calls the largest percentage of people might get through is, okay? So here's what we're going to do. First, we're going to find the mean. Then, of course, you have to find the variance in order to get the standard deviation. So first thing I want you to do, go ahead and find the mean from this distribution. Again, the mean is multiply them and add them up. Okay, so go ahead and find the mean. Actually, just go ahead and find the mean, and then after that, find the variance, and then after that, find the standard deviation. And then I'm going to show you how to use the standard deviation to help us actually answer this question. Go ahead and round it to the nearest tenth for this problem, okay? All right, what did you get for the mean? 1.6. Yeah, let's round it to the nearest tenth. Okay, so you should have got 1.6.
For both of them, round up?
Yeah, let's do everything to the nearest tenth for this one. Okay, let's just do nearest tenth on this one. Okay? So now the only difference for mean and variance is that you square the outcomes on top first before you multiply. Add them up. Did anybody do that one yet? 1.3.
For what?
I got 1.2.
Wait, for
It's 1.26.
Are you sure?
For what?
If you use 1.6, okay, you should have got 1.23, so that's 1.2. Okay? Then the square root of that is the standard deviation, okay? We're gonna call it 1.1. Now, here's the thing. Here's why we're gonna use this, okay? Remember that the standard deviation, do you remember Chebyshev's theorem?
No, oh God.
1 minus 1 over k squared. Remember that 2 standard deviations meant that at least 75% of the data was contained within those 2 standard deviations. Okay? So let's remember that. So write that down if you don't remember it.
Say again.
Wait, so
It's right there. It's right there. So here's why we need to know this. Okay?
wait, I still not get. I don't know if I got that wrong.
In order to determine if 4 lines is the right number, okay, if inside of that 75% of the data it's already way over 4, then we don't have enough phone lines. If it's under 4, then that means there's still room to use more phone lines. Okay? And if it was over 4 in 75% of the data, and then there's a bunch of data sort of missing from that area, then we know that it's not even close to being usable. But if it's under 4, then we would say, okay, at least 75% of the people are going to be able to get through with 4 lines. And that's the data that proves that the number of lines is useful. Okay? So here's what we have to do. We have to take 2 standard deviations above the mean. Okay? So what is 2 standard deviations, first of all?
2.2.
2.2. So what is 2.2 above 1.6?
3.8.
3.8. Okay, so here's what this is saying. Okay, that number is under 4, and they have 4 lines. So what this data supports is that if at least 75% of the people can get in with under 4 lines, obviously there's no such thing as 3.8 phone lines, right? But this number is under 4. So this supports the idea that 4 lines is probably enough, okay, because it doesn't go over. And that's what the point of this problem was, okay? So they shouldn't need more phone lines because we're still under there.
Here, so how do you know that it's...
So let's talk about expectation or expected value. And for the most part, what we do with expected value, we're talking about money. And as a general rule, okay, expected value is about probability of gain minus your initial investment. Now, I'm going to tell you that the book explains this problem 2 different ways, or they explain expected value in 2 different ways. I'm only going to choose to explain it one way because the way I explain it I think is easier, but you are certainly welcome to investigate the rest of that on your own and look at the other way that they explain it. I think it's more confusing. I think this way of thinking about expected value is the easiest way to think about it. We're going to look at 2 problems, and hopefully from that it'll make some sense, okay? So, here's the first one. So we're talking about a raffle to win a color TV that's valued at $350. Raffle tickets are $1 a piece. What's the expected value of the gain if you purchase 1 ticket? Now, what we're going to do is we're going to find the probability of winning of the gain, okay? In this case, the gain is winning the TV, right? If you buy 1 ticket, what is the probability of winning?
1 out of 1,000.
1 out of 1,000. So my expected gain, and this ties back to probability distributions, is I take that outcome, which is a $350 TV, and the probability, and I multiply that by the probability of winning it. Okay? And then I just have to subtract off my investment.
Can you show us?
I'm going to. I just want to talk through it first. And again, so again, here's the talking part. Here's the math part. We're taking the expected outcome and multiplying it by its probability, what we've been doing before, and subtracting off the initial investment. So what that looks like is this. My probability of winning is 1 out of 1,000. I'm winning, my gain, my outcome is that $350 TV, and then I subtract off the dollar that I invested. Okay? So the likelihood of my expected value is not going to be a win, right? If my probability of winning is 1 out of 1,000, we expect to lose. because the probability of winning is very low. All right, so what that looks like then is that I expect to lose 65 cents. Okay. The next problem is a little trickier because there's more involved. There's more than one option. There's not just one thing being raffled off, so to speak. Okay, there's not just one prize. Okay, in the next example, there's more than one prize, so we have to account for that. So here's the next example. Still 1,000 tickets. There's still $1 a piece, but now there's 4 possible
Why would they do
outcomes. I could win 4 possible prizes.
For what reason?
Except, how many tickets do you buy?
4. So you 4 were.
How many tickets do you buy?
Or wait.
1,000 tickets are sold.
2.
2. You buy 2 tickets.
2.
So the probability changes.
So 1.
Okay, your probability is not 1 out of 1,000 anymore. Okay?
It's 2 out of 1,000.
Correct. Okay, so let's keep in mind a couple things. It's not weighted. The probability of winning each of these prizes is the same. Okay? But because I bought 2 tickets, my probability is now 2 out of 1,000. So here's what it looks like. 2 out of 1,000 times 100. Plus 2 out of 1,000 times 50. Plus 2 out of 1,000 times 25. And if you wanted to reduce that down to 1 out of 500, that's fine too. 2 out of 1,000 times 10. And then I subtract off what I spent. Since I bought 2 tickets and they were $1 a piece, I spent $2. Again, we expect the expected value to be negative. We expect to not win. Okay, so when we go through and do all this, you should have a negative number, but it's not going to be that far in the hole or anything like that. Okay? Yeah. Negative 100, negative 100. $1.63. So yeah. Okay, so expected value, again, if you use my way, I'm telling you, if you look at the book and look at the way they do it, it's going to be a little confusing. I think the way I show you, which is the second way they show you in the book, is easier to understand. Okay? Questions? Don't have them. Any questions about anything? Okay, make sure you get those formulas down. We're going to work on 5.2 as well tomorrow, so we'll get a couple days at it. 5.1 was super easy, and then we'll have a quiz on Thursday. And then a couple things.